Good afternoon, evening. Since the time change, it looks like evening. And since I rode my bike today, it will be much cooler riding home. But I looked at the thermometer or the prediction, and it's only supposed to be down to 52 by 8 p.m., so that's not really too bad. So what are we going to do today? We're going to spend a lot of time with random processes. We're going to talk about things in the project if you want to, and then we're going to see some demos, and hopefully we'll get all the way through the quantization effects and modeling that are needed in Chapter 4 to work the rest of the problem set number 5 problems. What I've done since last week, took a break from grading, but instead of actually grading, what I did was I totally polished up the set number 5 solutions and got them in good working order. I reworked and worked the project problems. I reworked some of the project problems, and I worked problem number 3, and that led to me putting up some patches. And I posted on that, but I didn't really say explicitly what I did. In the case of problem 3, I rewrote my sentences of part A, B, C, and D. There were bad grammar in there, so I tried to make that more explicit. So make sure you use the newest copy that's up there. Don't look at an older one that had some kind of funky grammar. The spelling maybe was okay, but I'm not the greatest at writing. I will leave a word out here and there. I'm one of those type of people that I'm so anxious to get it in that all the words that don't show up are in my head and they don't get it typed into the page. And then I reread it and I say, what? I left this word out and that word out. You'd think I'm not an English speaker or something, because generally it's the little words that I leave out, but they make a difference, obviously. Okay, so we're going to start with the lecture material, and then we will jump into looking at Python as well. So I'm going to move over to the corresponding section in the notebook. There's a review of problems 1 and 2 on the project in here, but formally, I guess my plan is to start here, but we'll see where we're at when we get there. So last time we left, we had an introduction to random processes, and this is just a total build-up from the foundations in probability theory, random variable theory, and then jumping to the random process. So the random process is a family of functions of time. It could be of space, it could be multidimensional, but it's complex enough to think of a family of time functions that are indexed according to a random outcome from an experiment. So you could just think, if you were thinking about data bits on the internet, let's say, streaming into your device, we could say that at one instant of time we're going to see a certain pattern of ones and zeros forming our data that we're looking at. At another instant or on another occasion, actually the random process concept is not looking at other occasions, it's just looking at possibilities at a particular instant in time. Like today at 2 in the afternoon, these are the bit streams. But if we could relive 2 p.m. on today in the afternoon and looking at the bit stream from the same source, we would see a different pattern, presumably. That's the understanding. But we can take and use that concept in different ways if we want to, but formally it's an ensemble of functions corresponding to the possibilities that could be observed in the random process. So the picture that I like the most is this one, and there's an appendix in the book. Appendix A is on probability and random variables, and I think random processes, maybe it's in B, or it's all in one chapter, but I like this picture, which shows that the underlying sample space that you trace back to probability theory, and if you think like I do in that area, you're saying that those outcomes chi sub I, 1, 2, 3, 4, 5, and uncountable infinity, or a countable infinity, I mean, could be all the faces on a die. They could be indexed according to the voltage across a resistor at room temperature, which has lots of variation in it due to random electron agitation. Or it could be bits. It could be an index corresponding to a stream of bits, a particular bit pattern. But at any rate, those indices then map out onto a function on the real line or in the case of us, it's not continuous, it's discrete, and there is an introduction to continuous random processes in the appendix that I put together for this chapter. But the discrete version has sequences which match exactly the notation that we've been using throughout the semester. So we've got sequence 1, sequence 2, and then you see the ... sequence I, and those form the ensemble. So the way I like to think of it, unless it's a finite ensemble, and most of the ensembles of possibilities that we have are infinite. So you could think, if you were standing here, you would say that the number of waveforms I'm seeing stacked up here could go all the way up to infinity and go all the way down to minus infinity. So you have to be able to think big and just think it could be just an infinite number of waveforms. Now, can you grasp that? I mean,
and these waveforms are like the noise?
Yeah, they could be noise samples. Okay. So you could visualize that there's an infinite number of combinations of noise samples that could occur. And if we just use the random number generator in MATLAB, Python, Julia, etc., we could see that happening. And actually, that's some of what you get to do in the homework. You simulate stuff. So, and also in the exam number 2. So we have interpretations on this ensemble, and I like the term ensemble because I play music. So when you play music in a group, you say you have an ensemble, right? You have a bunch of players, and you're all producing a different stream of musical sounds. So this matches my understanding of ensemble. Are you okay with that idea? That it's just a collection of waveforms corresponding to the possibilities of what we might observe. So if we look at it horizontally, which is down below here, there's these 4 interpretations. So looking at it horizontally, you could say that a single time function would just be slicing across the ensemble at any particular waveform that we might decide to choose. If we wanted to slice it vertically, then we would be slicing it like I drew last week, either at time index where the blue line is or time index where the red line is, and that would be then characterizing it as a random variable. All the samples that we would observe at the blue slice would form the possibilities for a random variable. Does that sound good? So how many random variables do we have in an ensemble? An uncountable number, or I mean an infinite number, because they could start way back here and go all the way out to infinity, if we wanted to think that way. So, because there's lots of slices that can be made. So that's the random variable view. And then the most simple view is to just zoom in on one point and say, all I care about is that. And that's just a number. It's no longer random in any way. It's just, I'm going to pick a sample function, I'm going to pick one time index, and I just have a number. So that also can be done. And all of this understanding comes from the context. And in the book, for example, or in my notes, I'm using what a random process book that I used to teach out of used. It always used a boldface, lowercase variable name, letter, for a random variable, and then if you extend that to being a function of time, then it's a random process. What the book will do typically is they will just say it's x of n, just like it has been for every chapter so far. You have to understand, based on the discussion, is it deterministic, which means is it known, like is it a cosine, is it a unit step, a delta, etc., or has it got some random behavior? So you have to get that from the discussion. So if I was teaching people that are in kindergarten or first grade or something like that, that would be fairly difficult. But by this time in your life, your brains are pretty well stretchable and pliable to accept a lot of different things. True? I mean, to a certain limit, right? Okay. So how do we characterize a random process? We can do characterizations just like we've done for random variables, and that's what makes the random variables so user-friendly. You've already learned that. you know that you can find the mean of a random variable, the variance, you can find the covariance, all these other things you learned about in prob and stats. The only thing we have to do now is we have to index it. So we have to take the random process at index n, which makes it just a random variable, and then find its mean, and we'll find the mean as a function of n. We can find its variance as a function of n. That's still kind of mind-blowing because it says we have mean and variance changing with time. Can we avoid that if possible? And it turns out, for the purposes of this book, we're making a lot of simplification. So we're going to be making a simplifying assumption, and I'll kind of work into that. I'll just say, for starters, though, if we could say that the random process was strictly stationary, then the property of stationarity in random process theory would say that as we slice here, 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 it never changes. It's always the same. It's not a function of time. Does that sound cool? I mean, that's pretty much where we're going to be. We're going to be backed off to a slight simplification from that. I mean, a slight less strong assumption, but we'll be pretty close to it. Actually, I'll tell you the name is down at the bottom of the page here, wide sense stationary. So the first new thing we want to define in terms of a random process is we have, if we form a random variable at time sample n and at time sample m, n and m, we define then what's called the autocorrelation, or the self-correlation of a sequence at index vertical slice n and vertical slice m. And formally, the definition of that involves making an assumption that it's a complex random process. In other words, our definitions can handle complex random processes. Most of the time here, we don't need the conjugate on there. And if it's a real random process, the conjugate doesn't change anything, right? But it's just setting it up so that you could handle complex signals if need be. Autocovariance is the autocorrelation with the mean subtracted out. So you would take and find the autocorrelation on x with itself. That's what the xx is down here. So the subscript is kind of redundant. It just says x with itself, and I have two variables in there for time. It's kind of obvious that I must be correlating two things, because that's what correlation means, one thing versus another. And you learned about that in prob and stats, and I think we think about correlation in our life. Like a good example, I'll use the example that Lake gave a little while ago about somebody running into a King Soopers front. Knowing that we have sort of a random process, that what's the likelihood that somebody's going to drive into the front of a store, you know, that could be a random variable, random process type model. And because there's lots of people running around that are not coupled into the sample space, that we might be imagining what's the possibility that one or more people were injured in this event. That would be a correlation idea, right? Given one thing is true and the store is busy, we could say it seems like there's a strong correlation possibility that somebody was bumped into. Is that good? I mean, we just use correlation a lot. I mean, when it gets cold outside, are you going to feel cold? Am I going to feel cold riding home in the wind? Probably yes. Well, I need to wear my gloves that have wind stopper in them, for example, or I'd like to wear them probably if that's the case. At any rate, autocorrelation of a sequence, and then we can go to the autocovariance where we subtract the mean away. And an important property of autocovariance that we can make is if the sample index is the same, in other words, n and n, that's saying the two vertical slices that we are making in this autocorrelation and autocovariance are on top of each other, then that becomes the definition of the variance. Just it follows together like that. If the sample points are together, it just so happens that the autocovariance becomes the variance. And the autocorrelation will be the squared mean, right? Because if we sample n and m, we'll get the expected value of x squared. So first set of assumptions that are, it's going to make life simpler is wide sense stationary. So like I was saying, if x of n is assumed to be wide sense stationary, then we have this nice simplifying assumption. It doesn't matter absolutely where the slices are taken in the joint moments that we're forming, x at n and x at m. All that matters is the separation. So if I move along and keep the separation the same, the statistics don't change. And that's a stationarity type property because it's saying statistics don't change with time, but they will change with time difference. And certain types of processes are well known for the characterization of what happens versus time, but when you filter something with a signal and you want to correlate the input with the output, you would expect there to be a strong correlation between the input and the output when the time slice differences are pretty much the same, but as you get further and further away, you'd expect that the memory of that filter, and I'll be more explicit on that momentarily, will fade away and we won't really see any impact from the correlation due to the filtering action because it has finite memory. So this is very nice, and everything that we'll be doing in all the modeling will, will break down to this. So that this makes it very familiar to you. The mean of a random process is just a constant, the variance is just a constant, and the autocorrelation and autocovariance will just depend upon the time difference between the slice where the slices are taken. Now to up the ante a little bit in terms of complexity, we're now going to not restrict ourselves just to random process X. We're going to consider a second process Y, and pun intended, Y. The Y will be the output of a system and the X will be the input. So we'd like to be able to see how that factors in. Or another example might be we have a receiver, radar receiver, comm receiver. We have a signal coming in, we have a jamming signal present, and then we have additive noise from thermal effects in the receiver front end. We can model then the correlation between the various signals that might be present. And generally, we make the assumption noise is uncorrelated from signal. In the case of a jamming signal, we'll probably make that assumption too, unless, of course, the jammer is very smart and decides to be a repeat back jammer, a jammer that might copy some of what you sent and then just throw it back at you again, only time shifted or something. Is that believable?
Yeah, I've heard of cross-eyed jammers.
What did you call them?
Cross-eyed jammers.
Cross-eyed?
It's a different kind of jamming.
Yeah, there's lots of jamming scenarios, and I know in the Army you've got all the geographical related stuff of being on the field, but in space you have space objects floating around. But I worked some problems in Army type scenarios for some project I worked on, and I specifically remember one scenario was we have a secure comms radio, but we made the assumption that the enemy got their hands on one of those radios and they took it behind their enemy lines, and now they were going to use it to pump denial of service attacks at this network. And that's not a good thing, right? Denial of service is a form of destroying the ability to use a network because you'll overload it with packets and then it won't be able to get decent throughput. It'll have high latency and things like that. So I worked with Dr. Chow, who has since left the university in computer science, but it was an interesting project that we worked on. I think one of the ideas was, could we put beamforming of some sort if we know the enemies in the particular locale? Could we make sure we have some sort of beamforming antennas or something to kind of mitigate their jamming us? Lots of different assumptions, though, in that area. Okay, at any rate, so cross-correlation has a real practical value. So here it's X and Y. In most of what we're going to do in this class, it's just going to be the input and the output. of a system, but it could be, like I was discussing, jamming and noise for sure. So X times Y conjugate, that's the cross correlation, and then if we subtract the means away from each of the signals, which is what is going on in here, there's X minus its mean and there's Y minus its mean, then that becomes the auto-covariance. So I think if there's anything, I'm just going to pause for a moment because we're just about done, except working some specific cases. One of the things that bums you out in the beginning, or at least it did me when I was taking the class a long, long time ago, is phi is used for autocorrelation and gamma is used for autocovariance or covariance. It just gets to be daunting because we have so many symbols. Other textbooks I've taught out of have used different variable names, but in our book it's phi and gamma. If a process happens to be zero mean, though, then phi and gamma are the same because there's no mean to subtract. And in most cases that we deal with here, the mean is zero. So autocovariance, cross-covariance are the same, and autocorrelation, cross-correlation are the same. So now we'll apply the idea of wide sense stationary, so we can have jointly wide sense stationary. Then when we find the expected value for the cross-correlation, we have, if they're uncorrelated, we have this statistical property that the expected value of the product is the product of the expected values. And this was something that I'm thinking when I taught random variables, or province stats for undergraduate ECE, I'm thinking chapter 5, but I don't know what that means anymore because that was just a few times I taught it, but it's where you get up to the higher order greater properties on random variables. They introduce cross-correlation in there, and you're doing regression modeling and things of that sort. So you're wanting to find the correlation between a product of X times Y, and you might remember uncorrelatedness. Does that pop up in your head, maybe fuzzily? No? But you could trace this back to random variables and just say, what's the expected value of X times Y? That's really what we're dealing with under the hood. We just have it cluttered up because we have the time indices in there. So if they're uncorrelated, then it reduces down to being just the product of the means. And if either one of the processes has zero mean, and this is frequently true in a signal plus noise scenario at a front end to a system, then uncorrelated processes where one or both are zero mean is just zero. So the term then is orthogonal. One process does not interfere with the other in a correlation sense because of this property. And when I was in school, the professor liked to use that notation to mean uncorrelated. And two vertical bars meant that they were orthogonal. Why did he use that notation? I don't know. But orthogonality of two vectors means zero, right? And there's something that we're not going to study in this class, but is discussed in random processes courses, is the idea that random processes can be viewed as abstract vector spaces. So in an abstract vector space, if you have two vectors in an abstract vector space, if they're orthogonal, then their dot product is zero. And in our case, the expected value of a product of two random variables, that is our dot product. I don't know if that grabs anybody to say that's true or nice, but I know in fields and waves and in physics, you have orthogonal vectors, so in random variables terminology, we use that same idea, only in terms of density functions. I'm not really going to go into any more detail on that, but it's fully developed in the statistical signal processing domain, how you can leverage that capability. So the last thing that we have is what about the power spectral density? We've had the spectrum of a deterministic signal, but when we have a random process, we not only have its autocorrelation, we also have its power spectral density. And they're related by the Fourier transform. So if we have an autocorrelation function of two random process x with itself, then we get the power spectral density of that process. And a significant thing here, which I'll elaborate on a little bit more, is the power spectral density can be estimated in the time domain as well, and we're going to be exploring that. The function simple SA, or simple spectrum analyzer, is exactly designed to find the power spectrum of a random process. It finds the power spectrum of a deterministic signal too, but it's especially powerful for random processes. And if you inverse Fourier transform the power spectral density, you get back the autocorrelation function. The book likes to use two notations. Capital Phi is like what a Fourier transform would be of some quantity. It would be become a capital letter. But if you're practically minded like I am, using a spectrum analyzer in the lab and something, P is the more common variable for power spectral density. So we have both letters are used. So we didn't give a name to the expected value of magnitude x squared at n, but that is very similar to the variance calculation we did before. So if you put in n equals n for any process that's Whiteson stationary, you will get n minus n, or 0. And then that, if you back that up through the definition of the power spectral density, is the power in the signal, the total power in the signal, and it's just integrating the power spectral density. And I think I've asked, did anybody take ComLab? And nobody did, but that gets explored in there. It gets explored in the lecture. It looks like John's not going to make it, so I'm going to take this so I don't forget it. And that's what you measure with a spectrum analyzer. And most spectrum analyzers give you the ability to integrate the power spectrum on the display, so you can make a power measurement right on the spot. Earlier we talked about the autocovariance at 0 just being variance, so that is the AC power. AC power and variance are synonymous with each other. Total power is synonymous with the mean square. So if we wanted to integrate the power spectrum, we'd have to subtract the DC power but in most cases of radio communications and so on, there is no DC power on the transmitted waveform, so that term generally is 0. Okay, so we've been through the statistical modeling of everything. It involves some expected value operator in all of these cases, and I guess I shouldn't really minimize it, but it is true that with the autocorrelation function, even with wide sense stationarity, this this still involves, take this for an example. If you really wanted to get hung up on this, what you'd have to do is you'd have to integrate minus infinity to infinity of I'm going to use f for the density function, but PDF on x and x together. So it would be two variables in here. It'd be x1 and x2, and it'd be dx1, dx2, where x1 is x at, and x2 is x at. Should be M, actually. I got this somewhat messed up. No, I guess that's right. So you're looking at something that looks fairly messy, but remember the rule of the unconscious statistician, or the fundamental theorem of expectation. If x of n plus m and x conjugate of n can be written in some other form, everything gets much simpler. We don't have to worry about the density function on x1 and x2. We just have to worry about the underlying components. And I will look at an example of that shortly. So I'm showing you this so you know formally this is what it looks like, but there's no instance in this class where you ever have to try to jump into something like that. And hopefully you're saying to yourself, thank you, I'm glad it's easy, because it's easy to put in the x's, but how do you get the density on x1 and x2? That's something that towards the end of prob and stats you went through transformations of random variables. I don't know if you remember that at all, but that's a really messy topic with integration and changes of variables and things. So we don't have to do that here because we can use the fundamental theorem of expectation. And just to refresh your memory on that, since that's not too far back, it's this thing right here. So we can just pump everything inside of this function. It will now be a function of x1 and x2, but this function will simplify, and then we'll just need the density in a simpler form. You might be thinking to yourself, I knew there was a reason I didn't like random variables that much, because it gets messy in a hurry. It can get really challenging to work. But if you use the fundamental theorem of expectation, things stay pretty nice. So we've talked about the modeling statistically, which is the theoretical modeling with expected values, PDFs, and so on and so forth, to get the autocorrelation, cross-correlation, the mean, and the variance, all involving the theoretical side. But what about the experimental side? That's what I think is really important about this. It's not just theory, because I like theory, but we have to be able to do something and go to the lab and make something and then take measurements and compare it to our theoretical predictions we might get from the statistical model. And don't get me wrong, I like both of them very much, and I don't want to only live with one, because they both have advantages in certain scenarios. And hopefully, as you go out and work in industry, you don't propose building everything and taking measurements on it because you only trust your measurements. You don't want to use any modeling tools at all. You've got to be able to be diverse in terms of your approaches to work things. But you should strive to say, okay, we're going to model it this way. We expect the performance to be thus and such. So now we'll build a small version of it, or a simplified version, and try to track our theoretical model versus the measurement model. And that's a good way to go. So moving in that direction, if we wanted to find the time average of a signal, we can do this first definition. Time average mean is just adding up a bunch of values in a measurement of some waveform, x of n, that's a random process, and we're going to average from minus L to plus L, and so the window has a total of 2L plus 1 samples. That makes really practical sense, right? I do that on the computer. I'd roll the measurements in, and I just do that average. And then, if possible, I'd let L go to infinity. This is saying the definition is L going to infinity, but we're going to back away from that in a bit here, saying, well, we're just going to have to go with a finite number of samples because we can't wait around and collect an infinite number. So the time average autocorrelation can also be defined in a like fashion. You take x at n plus m, so it's like you have a bunch of values in x, and then you can shift it so that the difference is m. So when you shift it by m, you multiply together where they're touching, and in this case that would mean where there's overlap. There won't be any overlap outside the edges, but you'd multiply the points together and add them up where they do have overlap. and then that would form your time averaged autocorrelation function. And as L goes to infinity, it should all work out. But just like I was saying, we want to replace it, and we want to work with a finite number of samples only. So first off, what are we not assuming, or what are we missing when we do this time average? When we do a time average, we're in the lab, we're taking a measurement, we're not working with an ensemble. We're actually only getting one sample function that we look at and take our measurements from. Our theoretical model has an assumption about an ensemble. So can we do that? In other words, can the ensemble averaging we were doing with the densities and so on be replaced by a corresponding time average over just a single sample function? Well, mathematicians have discussed that and studied it. So if a process is mean ergodic, and that's a big name, it's a mathematical thing. I didn't come up with it. I had to get my brain around it. Mean ergodic just says the statistical mean and the time average mean are equivalent. We'll be making that assumption here. If the process is correlation ergodic, then the statistical autocorrelation and time average autocorrelation are equivalent. So pretty much we're checking two really important boxes here in our assumptions. So fundamentally, anergodic processes have to be wide-sense stationary as well. So we've got the ability to exchange the time average with the statistical averages. And then the only thing we have to fight our way through is the fact that we're not going to be able to let L go to infinity. So what will happen is, if we're going to go after the mean of a random process, its variance, or its autocorrelation function, we're just going to use L samples, and we're going to end up with what's called an estimate. And you know what I mean by an estimate. You're taking a measurement, and it's not perfect. It has some error in it, but you have a bound on the error. So you say, we're going to take 10,000 samples, or in Python, you'll maybe run 100,000, let's say, because you can do it fast. And you'll figure that that's going to be good enough. So in the case of the autocorrelation function, for example, if you just do what I pictured up here, we're assuming 0 outside the interval, so we end up with a bias in the measurement. So the measurement is biased for L being finite, in which case then we have to scale by this L over L minus absolute value of M for particular values of M to make the estimate be unbiased. And I put this in the notes because at a young age in my working this sort of stuff, statistical signal processing, I was reading papers and things on autocorrelation function estimation and then spectral estimation and how all that stuff related. And they always talked about the unbiased versus the biased estimator. And what you ran into this when you got introduced to the sample mean and the sample variance in prop and stats. Does that bring back a memory? Remember, when you do a sample mean, you sum up capital N samples and divide by N. When you use N samples to form the sample variance, what did you divide by? N minus 1, I think, probably. That's the unbiased estimator. I mean, you know it's one less than that. I'm never going to forget this, probably because my wife, who worked for FedEx in her last job, was working on a team where some calculations were being done for whatever it was, and she got into a discussion with her team about how they calculated the variance. One was not biasing, and the other was biased, had the bias measurement. And so they had to come to terms with that. Is it 1 over n minus 1, or is it 1 over n? And she argued in favor of 1 over n minus 1. She ultimately convinced them that that was the right thing to do. But in the case of this autocorrelation function estimate, what I learned a long time ago, and I still got those books in my collection, using the unbiased estimator turns out to not be as good a practice because you can get unstable results. So using the bias estimator actually was recommended in some of the algorithms I was studying. The bias is the worst at the tails because when you go out to the tails, you don't have a very big overlap. But I'm only kind of bringing that up because your intuition says, I don't want anything to do with a biased estimator, right? That would be your feeling. It's like bias in our society is not a good thing. But in mathematics and signal processing, we have to do what's the, what gives us the best performance. Okay, so the last thing we're going to do before we get into a kind of a applications area will be, what about random processes going through linear time invariant systems? So suppose we have this X is a random process by context. It's said to be a random process input sequence. It's going to go through a filter with impulse response H of K. It's going to produce an output Y of N. Now, H of K is an impulse response. Is it deterministic or random? I'm just trying to fool you. If we design a filter and set the coefficients, it's deterministic, right? It's just a set of coefficients in an impulse response. X is random, so Y is also going to be random because it's going to inherit that randomness from X. It's just going to get filtered by a set of deterministic coefficients, H. So if we go through our definition of the mean of a Whiteson stationary process, we'd be finding the expected value of the output of the convolution sum, and the expectation operator is weighting things with a PDF. That's what we're kind of hiding here with that expectation operator. But because H is deterministic, it's only seeking out the randomness in there. It doesn't care about the constants because linearity lets them pull through. So here we have the expectation operator hunts down on the inside of the curly brace the random variable, random process, and it then says, oh, that's just this constant if it's Whiteson stationary, mx. So that tells us a very nice formula. It says the mean at the output of a filtered noise sequence is going to be just the sum of the impulse response times the mean of the input. Then we're going to have a theorem that I think I don't introduce until you do the next exam, but it'll get defined in the exam because you don't have any homework problems that use it right now. But at any rate, there's one for the variance too. So now that I've got you thinking about it, no, I didn't do this right. Not important at the moment, but if we were sending signal through a filter, so the results that I end up talking about later when you do exam 2 is if you want to get the variance at the output of a filter and you know the input process X is white noise, which is about to be defined, then we can use that formula. And that formula in the red looks pretty similar to the mean, except that we're taking the magnitude squared on the inside, but we're still summing over the impulse response. It's pretty nice little formula, but it only works if the process is white noise, and that'll be better understood here shortly. Okay. So now we've looked at the mean. The mean works out to a really nice value, just the mean of the input times the sum of the impulse response. No absolute value on the impulse response. We get what we get by just summing the values themselves. So now what about the autocorrelation at the output? This is messier and I'm not going to try to prove it. It's in the classes that I would have taught on random processes, but the formulation goes like this. If we want to get the output autocorrelation function, y with y, we have to take the input autocorrelation, which is involving x with x, convolved with the time-reversed impulse response, and then convolved with the impulse response. I can explain why the double convolution in there, because y would be x convolved with h. So there has to be two convolutions in there, because to go from phi xx to phi yy, I have to take the first variable in phi xx, convolve it with h, and then the second x in that phi has to get convolved with h again, but because of the variable differences n plus m and n, it works down into that formulation in the blue box. I'm just telling it to you. I don't want you to sweat the details, but I do want you to appreciate the fact that there has to be two convolutions. And it seems like a bummer, but it is what it is, because it's the way the autocorrelation function works. It's expected value of the product of two waveforms. So we can actually write that as the convolution of phi xx and a deterministic function called C of L, which is called the autocorrelation sequence of the impulse response h of n. And that would just be this part of the expression from up above. And if you look at that in the z domain, and there's an example of that coming up here in the notes, you just have to inverse z transform. You don't have to use this in a homework problem, although at one time I had assigned a problem where you had to use that. But even if I would have assigned it, it's already worked out in the notes. If it shows up in the next exam, you'll have open book, open notes, so you'll be able to take a look at that. So when we plug this stuff together and want to go to power spectral density, that would, at the output, that would involve all of this, and then Fourier transform of those two convolutions, and then you'd be able to break those convolutions into the products of Fourier transforms of the three elements. We get this extremely powerful result, which says that the power spectral density at the output is the Fourier transform of that C function, our correlation sequence, times the input power spectrum. But in reality, the most important part of this definition is just right here. This is one that you'd use in the lab a lot if you were taking the comm lab. You'd realize that if you pass a signal X through a filter that has some magnitude response, that is the spectrum that you see at the output, just the spectrum of the input times the magnitude squared of the filter. And I actually think that you'd probably say to yourself, of course, that makes sense, doesn't it, in a way, that it shapes the spectrum. I didn't mention, and I haven't mentioned, although I should have, the power spectral density is a non-negative quantity. So if you have a signal generator producing some waveform and you want to estimate its power spectral density, it's delivering that power spectral density, say, to a 50 ohm load. I'm thinking of going into the lab now where you have a generator that has a 50 ohm source impedance, and then you're going to drive it into a spectrum analyzer that has a 50 ohm load impedance built into it. And the waveform you see on the spectrum analyzer is its power spectral density. For every frequency in the power spectrum, a property of the power spectral density is it has to be non-negative. If you're a purist, you would say, of course, because if a portion of a power spectral density was non-negative, what would that mean? Rather than delivering power to a load, it would be supplying power back out again. If we had such a device as that, I think we'd have free energy or something. I mean, there'd be something really bizarre going on if that was really true. So power spectral density has to be non-negative. It doesn't have anything to do with probability densities being non-negative, but it's just a physics. I look at it as being a raw physics kind of a thing. Does that Is everybody okay with that? There's a lot of definitions here, but there's just a lot of practical things that you may not bump into these right away in your career, but sometime or another you might be confronted by them. So, but this blue boxed equation is probably one of the most important ones in this whole section because it's a nice and easygoing thing. Just get the magnitude squared of the filter's frequency response. It'll shape the spectrum coming out from the input. What did I have to do on my space radio when I was working on part of the transmitter? Remember I talked about the NTIA last week and having to meet the NTIA spectral mass requirements. So I just had to come up with a filter design that could shape the raw transmitter output, remove some of the side lobes on it so that it would fit into this mass that the NTIA provides for spectral emissions. And that was just taking the filter, taking the magnitude squared of what I designed, putting into it the theoretical spectrum, and seeing that that worked. And then when they got the transmitter working, they had the transmitter with that filter in the FPGA producing output on a spectrum analyzer. They took a set of measurements, they sent them to me in a file, and I overlaid them on top of, what I had predicted, and we were good to go. And even though I haven't been working on the project anymore, my understanding is they've been doing more testing in that area just to see that the filter that was designed to meet the requirements is holding up to the intentions. Again, if you're building something, it doesn't matter whether it's radios or not, you still have to meet requirements, right? Safety, emissions, whatever the factors might be. So that was a cool little exercise here. And my manager helped me a lot because he said, don't get very sophisticated in your filter because we don't have much processing power in the FPGA to dedicate towards this filter design. So it was a cascade of moving average filters. It was something that was pretty simple to implement in the FPGA, not an elaborate high-order Butterworth or Chebyshev or Bessel filter or something. Okay, a special type of noise that we bump into and we'll be using in some of the modeling today is white noise. White noise, the term white noise is just based on white light. White light contains all frequencies or all colors of light. So if a signal is white noise, it means it has a flat or constant power spectral density. And thrown also into the definition is the fact that the mean is equal to 0. But the whiteness comes from having a delta function be the autocorrelation function, so that when Fourier transformed, the height of the power spectrum just becomes sigma sub w squared. Good? I can imagine somebody saying, that's not good. So what do we have if we have shaped noise that's no longer white? It's just called colored noise. And that's just kind of a physics idea too. It's got coloration to it because it's no longer flat. Now, a fact is that white and Gaussian are unrelated random process properties. One is the flatness of the spectrum, which relates only to the autocorrelation function being a delta, and Gaussian has to do with the underlying statistics of the values in the random process. Like, is it coming, in our case, from a random number generator that's Gaussian or uniform? In a physical setting, if it's off a receiver front end, the central limit theorem has made it look Gaussian because it's a superposition of all these random electron agitations. And you learned in problem stats that if you convolve a PDF with itself over and over again, it eventually becomes more Gaussian shaped. Is that in your memory from that class? So that's where that comes from. So this picture is just a reminder of how that works. In the case of a physical, real-time white process, we can't have flatness for all frequencies because that would say that generator is putting out infinite power, because we've already learned that integrating the power spectral density gets us back the power. But in the case of DSP, it's always periodic, so if we integrate from 0 to 2 pi or minus pi to plus pi, just one period, we're going to have a finite amount of power that will collect into that spectrum. So what I do at this point is I go off and explore a little bit in MATLAB, and I could have done it in Python. I just was lazy when I rewrote my notes. I didn't work everything over to MATLAB, or to Python. But before I do this, I just want to explore a little bit. And it looks like John may have written to us. Says he's studying for a midterm. Okay, so I'm going to go look a little bit at what we can do in Python before we actually go into this little demo stuff. So random variables. I said PyLab in there because I used to import PyLab. I just import NumPy and Matplotlib, but if you want to do more exotic things, you can import scipy.stats, and that gives you a huge wealth of functions which we don't need to use. But if you wanted to do that, like I did earlier today, if I put the tab in here, well, I guess if I put the period and the tab, it'll just tell you what all the different things there are in that module. There are a lot of really nice things in there. Things that we don't have any need for right now, but what we do have already available to us, though, are things like mean and variance and covariance. So we have an STD for standard deviation. So we can use those already from NumPy. So when we want to get random quantities, we have to go into a submodule of NumPy, and that is because I've imported all of NumPy, it brings in the submodule named random. So in order to see what random has in it, again, if I just do a dot, I will see what are the various random number generators. So the two that we're going to use, which are pretty lame, are rand and normal. So we have the normal, and well, rand n is all we're going to use. Rand n and rand. Those are the only two that we're going to use, but there's a lot of others in there. It used to be that those two were brought up to the top level in NumPy, but then they decided to partition them away. So in order to get access to them, you have to prefix the functions with random. So here I'm creating three types of random vectors, random arrays of 100,000 samples. Rand is uniform on 0 and 1, and so here I'm just going to shift 1/2 away from random numbers on 0 and 1, and I'll have numbers on -1/2 to +1/2. Same for the second one. Third one, I'm not shifting it, and the fourth one, I'm scaling by 5 and shifting by 3. So here I can plot the various scenarios here. I'm using the hist function, which is part of pyplot. I believe I put in the random variable, this array, and then I say how many bins do I want, and then I like always normalizing the histogram to a PDF. So remember what that means from province stats? If it's a PDF, the height is scaled to be probability per unit distance. So it's not the number of elements in that bin, it's the probability associated with that bin. So here I made 50 bins. So when I do the hist on x2 and say density equals true, I'm getting 0.2, and what's going on there is if I take the density height of 0.2 times the width here, which goes from 3 to 8, that should be 1. So I have 5 in there. 8 minus 3 is 5 times 0.2 is 1. If I picked a different one, like x3, now it's just going to go from 0 to 1, or x1. It's just minus 1/2 to plus 1/2. What do I know about uniformly distributed random numbers? We know that the mean is the center of the uniform distribution, right? So for this plot here, it would be 0. For the others, it would just be the center. And the other thing that I know from undergraduate province stats is that the variance of a uniform random number is always the width of the distribution divided by 12. Does that tweak your brain, or did you just plain remember that? So if the width is 1, 1 over 12 is 0.083, and if I go ahead in here and I'm just going to use variance, the variance operator, which is available when we import all of NumPy, you see the numbers match each other pretty well. So what would happen if I put in 3 in here? x3 is the one, or x2, I guess it is what I want to do. What should we be getting for this one? Variance doesn't care about a mean shift, so the 3 doesn't factor in, but we're going to scale numbers that run from 0 to 1, or have a spread of 1 by 5, so we're going to have a width of 5. So the formula is delta squared over 12. So what is delta squared over 12? I can just, well, I'll just do it here. There's my answer, but if I want to compare it, it's no longer 1 over 12, because the width of the uniform is now 5 points wide, so I have to put in, rather than 1 squared, it's going to be 5 squared. Look good? Look at the two numbers are pretty much the same. 2.079, 2.083. I'm running 100,000 samples, so I'm getting really good statistical accuracy. Now, if you want to compare two arrays, one to the other, I'll compare x1 to x2. So this cove function is going to compute variances and covariances. So if I look at the help for it, it tells you what the 4 entries are going to be. It's going to give a 2x2 matrix. And this 2x2 matrix is such that the first element is the variance on the first element, x1. The second column will be the cross correlation between x1 and x2. The next row will be the cross correlation in the opposite direction. And then finally, the fourth element will be the cross correlation, or the correlation of x2 with itself. So when I run that, I get, the variance on x1 and x2 along the diagonal, and then these numbers that are on the off diagonal should ideally be 0 because there's no correlation, but there's, randomness, finite number samples. Question?
What is the button that you push to see the detail on the...
Oh, Shift and Tab. Remember, I've been doing that all along. Whenever I have anything, I can go Shift Tab, and I will get the help for that function. What does tight layout say? If that makes any sense to you, to exclude an artist is a term for how it's drawing the picture, on the axes from the bounding box calculation. All I know is that it cleans up the plot if I don't use it. I did demo this once before, didn't I? If I turn that off, they tend to be all squished together is what happens. And this, with the tight layout, if you have an axis for each of the individual subplots, you will get space will form there to put the label in here without, and if there's a title on each of the plots, everything will lay out nicely. And then you want to do that if you need to do that for some result you're putting up in your project or homework. Okay, the next topic, and basically is jumping us back over to what the MATLAB has done, but I thought I'd just show you that if we wanted to do what I did in MATLAB, I generated 10,000 samples of uniform and 10,000 of normally or Gaussian distributed. And if I draw the picture of that here, first I generate them, then draw the picture. Things don't look as nice as they did with 100,000. That's why the uniform is not quite flat and the Gaussian is kind of bumpy looking too. I could change that, but I did this in Python just to match what I used in the example in the notes. What I'll have to do though, and what I do in the example we'll start with after the break, is I normalize them. The variance of these two are not equal. If I go to look at what they are, the uniform is just 0.08, whereas rand n, you might remember from MATLAB, always produces a unit variance. So what do I have to do to make that match? I have to go delta squared over 12. I have to go the square root of 12 over 1. So I'll take those values that are uniform and scale them, and now they're equal variance, at least in this calculation down here, because I did the scaling in this variance calculation. That's the starting point for the example in the notes, is to make them both have equal noise power for the calculations that follow. There's functions in Python that do auto and cross correlation, just like MATLAB has them. And I did some filtering in here too. I wasn't planning on looking at this because I was just going to look at the MATLAB example, but it is in here. I really want to get back to this when we come back from break. When we eventually go through quantization noise, you have to do some of this in homework from set number 5. So that's the next entry point for Python. We're going to go look at this example, but it's about 5 to 6, so about 10 after 6, come back. Or stay here if you want to relax. I'm going to put this on pause. Okay, we're back from break. We could have a longer break, but John, you're not here, so I'm just teasing. We're ready to go again. And the sooner we can be at a good stopping point, we can leave. So I'm okay with that too. So I'm just going to kind of overview what's in this example, because it's trying to show you differences between white noise, or what white noise does for a model, a simulation model, and then look at how it being Gaussian or being uniformly distributed doesn't really enter the picture in what's going on here. So here I generate a short number of points, only 4096. So when I did this, it's a long time ago, I didn't want to make a very long vector. So what I had to do, generate Gaussian of zero mean and unit variance, and then I wanted to generate a uniform distribution that ran from minus square root of 3 to over square root of 3. And if you think about how that works out mathematically, that becomes 1, you would say, like we've been talking, delta squared over 12. That's what we'd be getting here. We'd be getting 2 times square root of 3 over 12, so that would be 4 times 3 over 12, which is 1. That just tells you that if I put things on equal footings, I should have unit variance in both cases. So I drew a picture of the Gaussian and the uniform, and they really look equally random, but the biggest thing you should notice is that the uniform seems more or less constrained vertically, whereas the Gaussian, we know the tails will go to plus and minus infinity, but on a short record, we're not necessarily going to see it jump really wildly. Next thing would be to do an estimate of the autocorrelation function. I did not show you the PDF or the histogram, but I did show you that in Python already. So for both distributions, being that the random number generators are assuming to produce uncorrelated random samples, if they're uncorrelated, then we would say that uncorrelated samples would be uniformly distributed, would be white, because there would be zero correlation with the zero mean process unless the lag was set equal to 0. So in both cases, the autocorrelation should be delta of m. So I used a function called xcore that MATLAB has in its signal processing toolbox. Python has it in NumPy, or NumPy.signal. It's got a correlation function, and then I have another one that I talk about in the notebook that does its thing. Just reminded me I'm going to be posting up a fix to the notebook for chapter 4 because I discovered an error with Python today. Not an error, it's just a syntax error in my notebook that I had to clean up. At any rate, I compute the uncorrelated, an unbiased autocorrelation estimate for both of them, and they both should be delta of 1. So I plot them versus the lag, which is as I'm sliding the one array versus the other and doing the sum of products. So they both approximate a delta function. That's as close as it's going to get. It spikes up to about 1, and then it hangs around 0 the rest of the time, meaning to say that it's uncorrelated. For the uniform and the Gaussian, it's very similar, not identical, but similar. And because these are estimates, the numbers are not perfect. It's not perfectly 0 when the lag is 0, and it is not perfectly 1 when the lag is 0. But it looks pretty good. So we get an estimate of the power spectral density using PSD, which is a function that MATLAB used to use, or I used to use in MATLAB. PSD is available in Python, and you see that in the notebook. I prefer the function simple_SA, and that's what I'm having you use in problem 2 of the project. It uses the same basic concepts, though. It's called Welch's method of averaging modified periodograms. I don't really want to go into the details of that. I have the discussion on all of this in a one of the very last chapters of the notes, which we generally get to go through. It's a function that will estimate the power spectral density. So here I'm having it estimate the PSD using a 256-point FFT, and I'm assuming that the sampling rate is 1. I think that was the third argument in PSD in MATLAB. And the PSD is pretty flat for the Gaussian noise, and then doing it for the uniform noise, the power spectral density, again, is pretty flat. It's got fluctuations around it just simply because you don't have a lot of samples. If I was doing this in Python, I would crank the samples up, and I do have that in that sample notebook, and you will be able to crank it up if you need to do a PSD at some point. Again, you're going to be doing that in problem 2, and you're going to be using simple spectrum analyzer, or simple_SA. So the next thing was to send the white noise through the a low-pass filter, and this low-pass filter is our very familiar equation from problem 3. It's just got different terminology. It's got a times y of n minus 1 and 1 minus a times x of n. In problem 3 of the project, it's 1 minus a, or 1 minus alpha, times y and alpha times x, but it's still a similar idea. It has unity DC gain, which you show in part A of problem 3. So if we wanted to get the theoretical autocorrelation function, we have to go from the formulas we were looking at before the break, where you have to take the input process X and convolve it with the C of L function, which is the autocorrelation of the impulse response with itself. That was this guy right here. And the way I get that C of L, and this was useful for certain homework problems, not assigned at this point, but I went to the Z domain, formed the product, and then I did the inverse Z transform, and I recognized that when you have, remember when we talked about Z transforms, you replace Z by Z to the minus 1, that was like the sock model, sock analogy. I was saying it gets turned inside out. So the region of convergence is the complement, and so the region of convergence ends up being, for one of the two sequences here, it ends up being magnitude of Z less than magnitude of 1 over A, or the magnitude of Z greater than magnitude of A. So you have an annular region. So when you inverse Z transform these two terms, you have to take that into account. One is left-sided, one is right-sided. And you know from your homework that that forms then an absolute value to cover the whole range of possibilities for M. And then that produces this scale factor that sits inside of this definition over here. And the cool thing about this is because the autocorrelation function is white going in, what I don't explain intimately is that this just becomes the variance of the white noise, and then you've got the delta of M minus. So what happens there is that convolution sum just disappears, because only when L is equal to M does it do anything, because the delta is turned off. So you just get sigma x squared times C of M. So I don't know if you notice that. That's like the expansion that's in this area right in here is where that expansion takes place. So that's the theoretical value for the autocorrelation function of the white noise coming out of the low-pass filter. And again, if I look at the autocorrelation function using xcore or core or whatever function I'd use in Python, I get a theoretical and simulation value, which are pretty similar for only 64 samples. And then if I go ahead and use this idea that the power spectral density at the output should be the white noise variance at the input, sigma x squared equals 1, and then the magnitude squared of the low-pass filter shape, and put that into a calculation, we see that it's a power spectral density of the low-pass filter magnitude squared, only plotted it in dB. That's the dashed line, and then the bumpy line is the estimate from the power spectral density estimator. But the shape is pretty much the same. It would become really, really exact if I used more than 64 samples. I was very cheesy. I didn't use hardly any samples in my calculation, so I got really noisy estimates. But the idea is there, that everything follows through. The other thing you can do, and this is more of a control systems idea, is you can use white noise driving a filter to estimate the power, to estimate the frequency response, because you can look at the cross correlation between X and Y, and if you go through the math of that, we see that the cross correlation will just be this sum of the impulse response times the times the autocorrelation of the input, and if that becomes a delta function, which it is for the white noise case, that is just sigma x squared times delta of, no, it's a constant, never mind, I don't need that in there. So it's just sigma x squared. So that says the inverse Fourier transform that to get the cross correlation back again. Let's see. That's just going to be whatever the variance of the noise was times the impulse response of the system, and if that is equal to 1, calculation is exactly an estimate of the impulse response, and it would contain additional components if it was a complex impulse response, but here it's only real, so it's just an a to the n u of n kind of impulse response. So this is, in control systems, this is called system identification. You have a system, you'd like to identify what is in the black box. You know, it's a linear system. You drive it with white noise, and then you record the noise at the output and correlate it with the noise at the input, a cross correlation, and then that can get you in the spectral domain what that cross spectrum is, and then inverse FFT that or whatever, and you get the impulse response. It's kind of cool if you're into system identification, which it shows up in applications more than just controls. It's trying to learn about something. Okay, so going back over to Python, there's really nothing else to show until we get to the quantizer, but I wanted to see where I did have the use of PSD. That doesn't happen until further down the road, so I don't really need to go look at that until I go through our application now. So the big thing we're going to do is we're going to say we've had a whirlwind tour of random processes and how statistical analysis involving expectation relates to the time average in the measurement domain, and looked at white noise going through a filter, and looked at autocorrelations and spectra, cross correlations and cross spectra. Now we're going to apply this to one specific area, and that is quantization noise. But then we're going to have other things we can do with it and take that sort of to heart when you think about problem 3 in the project, because that is a noisy signal going through a smoothing filter, and what we're capable of doing, and how theory could be applied to that in a lot of ways. I'm having you do a minimal amount of theory. You're doing mostly just measurements. You're setting up a simulation, taking some measurements. So the first thing, this is jumping back into chapter 4 formally, because what we just came through was a diversion to handle things in probability random variables and random processes that were distributed into chapter 2 and the appendix A, and I saved them up for now, and now we can jump right in and make use of it in an application. So I have a bunch of writing there, but really the writing is all of this. So the writing is shown in a picture form. We started off with this simple model, input with a C to D discrete time system and an output. So now we want to enhance our model. We want to say our C to D is kind of artificial. It doesn't have, it's very idealized, so we're going to put in a true anti-aliasing filter. We're going to put in a sample and hold circuit, which will be in the electronics, and we'll put in an A to D converter. So that will be 3 components to think about in the modeling. Most of all this stuff kind of drops by the wayside, but we still have it hanging around. And then at the output side, we think of our D to A converter followed by an analog reconstruction filter. And you did see reconstruction filters last week in that demo of the 4x oversampling in the compact disc player. Remember that? We upsampled, and we're going to see that in more detail here for a more general case. So everything's going to be taken in order. So the very first thing will be that, and then it will be sample and hold. And then when we get to the A to D, we'll talk about quantization noise. And then after that, we'll talk about eventually the reconstruction filter. So first thing is how to avoid aliasing. We pre-filtered the signal when it comes from the analog domain. We have to think about a realizable analog filter and how best to do that in our system. And it's very easy to get carried away. I can remember back in my early days of capstone design, having students work on a project that was to build an analog and anti-aliasing filter, very simple in terms of what we can do today, but they ended up building their filter with op amps, and they had to build like a 10th or 12th order filter with op amp active analog filters, and they had a tendency to oscillate very easily on a breadboard, so they were challenging. But we want that filter to get rid of the spectral content so that when we sample, we don't introduce any aliasing. So ideally, the anti-aliasing filter passes everything up to the folding frequency and blocks everything beyond that. But a realistic filter has got some response in that interval, and maybe we're willing to assume it's zero, but this was just saying if that anti-aliasing filter was perfect and it perfectly eliminated components above the folding frequency, our effective response would be whatever that h of e to the j omega system is in terms of the analog domain, and we looked at this earlier. But the book brings up the point that in reality the analog anti-aliasing filter is not perfect. It's only an approximation to its response times the digital filter's response, and because some aliasing will exist, we're going to get a term out here that's called anti-aliasing signal or alias signal and alias noise coming through to the output, not perfectly eliminated. We'd like it to be small, but it can only be so many dB down is the terminology that gets used, and you're familiar with that from analog electronics, right? You have so many dB down outside the passband, and maybe you want that to be 40 dB down. What do you think in digital filters? We generally are looking for 60 dB down or more, just depending upon the application. So building this higher order filter that can drop all of the spectral energy from our input signal, the harmonics and things that can only get in and cause aliasing and then fold back down into our spectrum and sort of disappoint us in a big way. And maybe I need to stop there and think about it. If I'm speaking with my voice, a low-pitched male voice, and I'm sampling at 22.5 kilohertz, or no, 44.1 kilohertz, so anything above 22.05 in my voice is what's going to fold around and come back in again. Now, if you take an infant or a female voice, which would be higher pitched than mine, then there's more of a chance. I don't think my voice has too many overtones that are over 22.05 kilohertz. But even so, musical instruments like violins and flutes and other instruments that play in the treble clef, they can produce overtones up there. And if they were to fold in, you could all of a sudden start hearing them. They wouldn't be the correct overtone. It'd be an overtone that you don't hear because it's above your hearing, but when it folds on top, it's going to be annoying sounding. And I used to have a really cool demo that I did of something like that, but I don't have the hardware to do that anymore. And what it was listening to a compact disc played back and then downsampling it without an anti-aliasing filter, and as you purposefully downsample it, the beautiful music of the CD sound gets all garbagey sounding when the aliasing happens. Believable? Or maybe you've heard it. There's probably a demo of that somewhere on the internet, but I used to do that in the lab. So if we don't want to build that really high order anti-aliasing filter, what can we do? And the big proposal that I'm making and the book makes is multi-rate sampling. So we consider that we have to get rid of signals above the folding frequency, but maybe we are trying to avoid this sharp cutoff high order design. And if you go with that single filter design just at the sampling rate, everything has to be rolled off to avoid aliasing to the desired level by omega sub n. So, and you can think about equalization. If you take out, you might take out with your filter some of the desired signal because you have to start rolling off before you reach the folding frequency. And then there's phase distortion, which is another undesirable impact. Phase distortion could color overtones from different instruments blending with phase distortion. So the fundamental thing is difficult inexpensive. And I can't say I was doing this stuff when this was in its infancy. I was in college when the compact disc player came out, so I didn't really have an appreciation for it. As a matter of fact, I didn't take any DSP until I was working on my PhD. I graduated with a background in microwave electromagnetics and just basic electronics, analog circuit design, and went to industry with that. And I didn't take any DSP because it was a very specialized class that only a few people would take, and it was known for its mathematics that typically blew people away very easily. And there was only a few books. The predecessor to this book is what was the dominant book at that time. But it was extremely mathematical, and it was kind of void of practical applications because there really wasn't things that people could point their finger at. Certainly not the compact disc. I mean, that's probably what got me so excited. And you can't be excited about it because it was there when you were born, right? You're not excited about it. Am I correct?
Yeah.
But what technology has happened since you've been growing up that did get you excited? And smartphones. How about radar in your car? You ever use that? Okay. Yeah, it's very pervasive. And when we had our first terror attacks and things, our airport setup changed dramatically. So if you travel, you didn't like it, but you knew that technology was helping us hopefully make it safer. But probably you're more cynical than I was in the beginning too, because after technology comes up, pretty soon it starts getting invaded by all the dark side, you know, the thieves and the criminals that want to cash in on it, just like, you know, stealing my bike parked out there or whatever might happen. That's so omnipresent in my mind. I think how great it is, but then very soon after that, you sort of see the opposite side of it, and you see, why did that have to happen? But that just happens. That's the way people are. So at any rate, I still get excited about this idea. So we could do a low-order anti-aliasing filter and then come in at a higher sampling rate and then make our digital filter have the fine-tuning for the sharp cutoff and then drop the sampling rate down. And of course, this would not be like this as a cascade. This would be some sort of polyphase implementation, so you're not doing all that heavy lifting before you downsample. That was something we talked about a couple weeks ago. So the book has this little example, and I mean, I have a bunch of bullet points out here, but I'm just going to go through and look at the picture. So suppose this is the spectrum of our desired signal. It's predominantly located in the band from 0 up to capital omega n radians per second. It happens to have some high frequency noise that comes along with the signal. It's not something we really want, but it's there. It's captured in the front end of the system. It doesn't talk about overtones, but that could be included in that. But if we had to do this without oversampling, we would have to chop it right off at omega sub n. But if we can do a lower order simple anti-aliasing filter, then it will provide a little bit of roll-off of our undesired noise out in here. And then what we can do is once we get it into this higher sampling rate, we can come along and build a digital filter that does a great job of cleaning it up. And yes, there will be some aliasing above omega sub n, but we've designed our analog filter to be good enough rolled off by omega sub c. And of course, that's shown as 0 here, but actually it'll be so many dB down, maybe 50, 60 dB down. So the folding that happens mostly happens up in here, and then we get rid of that, and then we end up, this is an idealization, but in the third edition of this book, they added in this example, and this was something I'd been talking about before then, but it's kind of a cute example of trying to motivate the idea that oversampling is powerful. I went ahead before this example, and I assumed that the spectrum of interest might have a Butterworth shape to it. It has a cutoff. It has a roll-off rate of so many dB per octave or decade. And then I said, suppose we're going to implement an anti-aliasing filter that's a Butterworth filter also. And then the idea is that I want to design that Butterworth filter so that it adds additional roll-off of the alias component so that it can drop so many dB down in the passband of the desired signal. So that was kind of the basis for it. I'm not really spending a lot of time on it, but I could go through the model. It's what I'd call a filter design problem. You're just looking at a filter prototype, which class did you do that in? Circuits 2 maybe? Or we worked with Chebyshev and Butterworth filter prototypes? Okay. So you could get revved up on this if you had to, but I just kind of sketched it out. And what you do with this sort of idea is you take, if you have a Butterworth, you can then push into that analytical model for the Butterworth and say, if that's the spectrum of my signal, that's also the shape of my anti-aliasing filter, I can spin that around, and I'm just kind of looking at the equations, and I can come up with a number. I can come up with the order of my Butterworth filter in order to get so many dB down at the output of the anti-aliasing filter, and that is this amount in here, I believe. So I can make a high enough order Butterworth anti-aliasing filter to make this happen. So I take a case of sampling at 1 megahertz, have a Butterworth spectrum, that's 350 kilohertz, and I want to be attenuated by at least 60 dB at the folding frequency. So I work through that, work through the equation, and I say Cn has to be greater than 16.2, so that means you have to come up to the next integer value. A 17th order Butterworth filter for this particular spectrum is pretty crazy. So first design is 17th order Butterworth and sample at 1 megasample per second. But if we're willing and able to sample at 4 megasamples per second, we can be really lazy and put a first order Butterworth up front, and then we can take care of the rest of it with a high order low pass filter. Again, the polyphase idea would be out in here. So that's kind of inspirational. And that's why I mentioned the senior design project from years ago, where they tried to do this all with an active filter, and it was about a 12th order filter, and it was very hard to do. And I was naive enough to ask them to do that, and thought it could. I knew it would be a challenge, but it was more of a challenge than I thought. These days, I wouldn't do that again because I know the technology is advanced, but it was picking up from the background that all EEs still get in analog circuit design. So that's just a little discussion about anti-aliasing filters and some trade-offs that have to go on. Chances are multi-rate processing is good. So the next step is to head into the A to D converter, and the first thing is the sample and hold. The sample and hold is generally there. It's generally, and if it's a fast converter, it might be a separate circuit out front. If it's a lower rate converter, it might be built into the A to D, but in any case, it's something that can take the input and hold it long enough so that the converter can go through its conversion process while the signal is standing still. Because if the signal is, moving around, you've got to do something with a sample and hold to say, hold it because I've got to take a picture of it. I'm going to hold it long enough that I can convert it to a binary code. So that's the nature of the sample and hold. So if you look at the model of the sample and hold, it's actually a zero-order hold in control systems or in electronics, where it's just an impulse response that holds constant for one cycle of the A to D converter. So if you look at the impact of that on the overall operation of the A to D converter, the zero-order hold just holds the outputs of the input so they can be converted, and it doesn't alter the input. It just simply, it locks onto it, holds it long enough. It probably only has to be a short period in here. Conversion is done, the digital word is written out from the A to D, and then wait for the next one to come along. So in reality, that zero-order hold doesn't really do anything bad unless it was imperfect or had droop or something like that, and that's certainly possible. It might droop. It might, when I say droop, I mean it might not be able to hold it. It might kind of drizzle off a little bit and cause some error. But the next simpler model is just assume that it's pretty close to perfect, and if it's pretty close to perfect, it really doesn't alter things. So unless you want to do a more advanced modeling of the sample and hold, we'll just assume that it's constant until the next sample, and we don't have to worry about it anymore. I'm saying your job might require you to drill into it, and I worked in some application areas a long time ago where I had to read about it. I had to read about my device and understand what it might or might not do. And then I probably checked out a book on details of modeling sample and hold circuits. But I don't know, as time has marched on, what I found is that everything in electronic subsystems, the experts design these subsystems, they'll talk about them in their data sheets. You're the designer that integrates all these subsystems into your electronic design. You know, it's going to be some analog and digital and RF. You don't have to drill into it because somebody else has done that. They've written their data sheets, so you might, get 3 data sheets. Like in a capstone design project, you might know that you need a component or a subsystem, and you just study them and see what's going to work for you. And I don't know, what have you done for you guys that are in capstone design? You generally have to have your design review, and you have to have at least 2, right? 2 components or a trade-off of some sort. Why do you pick one versus another? Cost, availability, and performance. And if I was doing this on a budget, it would be cost would be the overriding factor. When I was working in industry, my very first job at Motorola, where I was working at surface mount components, chip capacitors, and other things of that sort, I remember the chip capacitor was something that was very important in my project, and I got exposed to the idea that I want this chip capacitor, but then I ran into the issue that everybody runs into, availability. Price was not an object necessarily, but availability was, and I had to hunt around to find somebody that could get me the parts fast. Has that happened in capstone design ever? It depends on what kind of design you're doing. The mundane parts I know are easy to get, but a lot of times I remember teams that I had would buy 2 of something, and I remember one semester they had built a little container for their project board, and it was plastic, and they put that board in there without appropriate measures, and they had a static discharge, and it blew the main parts of the board up. So one of the team members went off and investigated some spray paint for automotive use that was anti-static, and they took that container and they sprayed it with that anti-static paint and then created a new board, mounted parts on it, and then it kept it from getting zapped. But they were very disappointed with that, for sure. So now we're going to move, talked about the sample and hold, so now we're going to move into the heart of where we get to have some fun with our modeling, analog to digital converter. So it's a cascade of 3 stages onto itself. It has the ideal continuous to discrete that we talked about early in the semester back in chapter 2. It has a quantizer, and then it has a coder. So the continuous to discrete is really just responsible for saying that the analog signal is a sample, and if the sample and hold is working properly, we have an analog sample. So we have the analog sample that's a copy of, at an instant of time, the analog input, and that's in the discrete time domain now, and now we have to quantize that. So quantization is a nonlinear operation, and the way it's talked about here, it's Q for quantizer. So it's the representation of quantization of a infinite precision waveform into a discrete time waveform of amplitude levels. So we could have uniformly spaced or non-uniformly spaced. Most everything that I work in audio is uniformly spaced, but if you're working on telephony, telephony uses companding, which is compression and expanding, and the telephone company, even back in the original days of analog voice lines, they used companding too, because they knew that there was crosstalk and other things that would happen over long runs of analog twisted pair. So the companding idea was to try to maximize the signal to noise ratio and not let the distortion eat you up. So we're going to look at the uniform quantizer, and that's how our quantization model is going to be developed. We're going to assume a bipolar input. So if you're working with an Arduino or some other microcontroller board, you might see that there's an A to D on there, but it might be a unipolar A to D. So unipolar A to D would be, say, take 0 volts up to 5 volts or 0 to 3 volts. Now, if you have an analog type waveform like audio or speaking, what are you going to do if your converter can only start at 0 and go to 3? You have to use some sort of level shifting in your electronics to move, your signal, which is bipolar, as speech is, and center it at a halfway point in the biasing. But I'm not going to really dwell on that. I'm just going to make the idealizing assumption that our quantizer is bipolar, and if it's not, we manage that. I worked a project with an Arduino. I published a paper on it, actually, that was a unipolar converter, but then in the Arduino code that I wrote, I had a bias that got put on and taken off again so that I could have analog input and analog output. So that was the level shifting operation. In the picture I'm going to look at here, there's 8 quantization levels, just because it's easy to draw the picture. So this would be the simple uniform quantizer, and it sets the stage for the terminology that the book likes to use. They talk about X max. So X max says that it's kind of a little bit, I think this is pretty good mapping. I guess I have 7 delta on there. So X max is 7 delta over 2. And then it's minus 9 delta over 2 for the min, but it's actually, we don't get that picky about it. We're just saying it's some positive swing and the negative swing is symmetrical. But on this picture, it's showing minus 9 plus 7 because we're having what's called a mid-tread quantizer, and that's the most common type that we use. We want to have a quantization level at 0. So if you have a binary setup where you have, 8 bits in this case, what are we forced to do? We're forced to put one of our quantization levels at 0, and then we have to have one more quantization on the negative side and one less on the positive side. That's just what you have to do. And you've all coded in C before, right? So you go minus 2 to the, say, 16 over 2 for the negative values, and then you go to 2 to the 16th minus 1, quantity minus 1. So That's why because you have one less level. But on the grand scheme of things, when you have a lot of bits, that one quantization level is minuscule, but it still does exist. Okay, so the mapping then, the favorite mapping is the 2's complement, and I'm not really going to go into that. I have it in the notes, I discuss it, but I realize that you have computer system stuff that you did in logic circuits, right? Somewhere along the line you've done this stuff. But 2's complement is what we're mostly interested in. There's offset binary, but 2's complement is what's used on our computers. And if there's bipolar things in converters, it's generally a 2's complement form. And I made that assumption in problem 3. So now we're getting close to touching problem 3 from the project, where we have the assumption of a 32-bit word, and we're using signed arithmetic. So the mapping is such that when we go from minus delta over 2 to plus delta over 2, that's going to be this mid-tread. And does that sound weird to you? Mid-tread, mid-rise? I'm talking about as a staircase. Mid-tread, you know, tread is where we put our foot when we're on a staircase. So we have a tread at level 0, we have another tread at a delta above that, and then we have one below that. I guess if you were walking from your basement to your main floor, our mid-tread is halfway up our set of stairs. Is that cool? I always think about that. Does anybody know what that means? But tread has to do with if you're a what's it called? In building a house, you have the framing team puts in the staircase usually, right? If you're talking about framing for a new house or something, they will install that, and they will have the treads on their staircase that they put in. So the mapping is to a code word in 2's complement form, and this is the way the book does it. B is the number of magnitude bits. And there's one sign bit. That's just the way you want to think of it. It's 2's complement or offset binary, but just think of it as out of the total allocation, there's B plus 1 bit words. So if we're talking about a 16-bit, and my pen is aggravating me because it's not drawing. So we've got 8 bits. We've got 15 bits for the magnitude and 1 bit for the sign. So the terminology that people use would be Q. This thing is so bad right now. It's because the video's running. I'm not a great drawing person, but this thing is just like stuttering massively. So I don't get any smooth action with my stylus. That's still pretty bad. That's supposed to be a Q, but it won't draw. It looks more like a circle. So Q15 refers to the fact that we have a 16-bit word, but we have 15 bits of magnitude, and we have ones offset to the side. That's our sign bit. And I still would like to, at some point, when we get way near the end of the class, I'd like to talk about a library that I've used and had fun with, but right now it's kind of a distraction. So that's why problem number 3 on the project is just straight binary. I'm just working with straight binary. I don't have anything fancy with it there. It's signed binary though. So we know the leftmost bit is the MSB, and it's also known as the sign bit. The rightmost bit is the LSB. And what we're thinking of here in our math modeling is we're thinking of a binary point at 1 bit to the right of the leading bit B0. So B0 is like our sign bit, and all the bits to the right of that binary point are our magnitude bits. In the business of fixed point math, people will have a variable number of bits. They'll scale it up and down, so they'll have 2 bits, 4 bits, 3 bits, whatever, to the left of the binary point, and then the remaining bits are off onto the right side out of 16 or 32 or 64 or whatever. There's all kinds of games that can be played in this library I'm thinking of, manages all that stuff for you. But in this development here in the notes, it's very simple. The total number of bits minus 1 is B, and that's how many magnitude bits we have. So our quantizer output is composed of a sign bit, which is an amplitude level that's either minus 1 or plus 1, and then we have a binary fraction as we count from 1 up to B bits, and the weighting factor is the 2 to the minus I. So this is our weight, our binary weight, as we go further to the right in the least significant bits. So our range in this model is minus 1 up to 1 quantization level less than 1. That's just because of, again, the mid-thread idea on the quantizer. This is just an example of 2's complement math, which I don't really want to discuss. I guess I'm not as great a source as probably your logic circuits teacher would have been. I mean, I'll deal with it myself as needed. And how do I deal with it? I use Python, because Python has great tools for working with fixed point signed arithmetic. So this just shows you how you could represent our 8 levels in our quantizer. We've got the negative values here, we've got the 0, and then we've got the positive values. And if we were to look at the impact of that on a waveform, say a sinusoid like this, this is just showing you that the ideal value from the sample and hold would be the black values, which represent extending the sample point on the sinusoid, but the dashed values represent the quantization error that is occurring because of our quantizer action. And this is an 8-bit quantizer, so it's gross. I mean, it's a large amount of error. Okay, now we're getting finally to the main punchline here for our model. How do we analyze quantization errors? We pretty much have 2 choices. We can do just the brute force simulation, which is very popular. It's very easy to do by today's standards. But years ago, people liked the efficiency of a back-of-the-envelope calculation using a linear quantizer model. So our quantizer model, our linear model, is to say that our signal comes in, and we're going to add to it a quantization error, which is going to be a random process, such that the impact of the quantization model is it outputs our true value, but it applies an error to that true value as a result of the quantization. So it's an additive noise model for the quantizer. And if you were building a numerical quantizer, which I have in Python, which you'll be using, it will form this error, but it will be time varying. It will change with every signal sample. The linear quantizer model assumes a random model, random noise model, additive noise model for E of n, and E of n is said to be a uniformly distributed random variable from -1/2 a quantization level to +1/2, and it has some simple modeling properties. It's said to be a stationary random process. It's a white sequence, and a very huge stretch of the imagination is this error sequence is uncorrelated with the signal itself. And in reality, it's not uncorrelated at all, but for a lot of modeling purposes, it's useful to be able to make this assumption just for simple calculations. So we assume that the PDF of the error is a uniformly distributed number, like RAND gets produced in Python or MATLAB. And this is the shape of the PDF. It ranges from -delta/2 to +delta/2, and delta is related to the x max for a quantizer. So if our quantizer was +1 and -1, then that would tell us that x max is equal to 1. And these are the types of things that I give you in the homework. So it's a good time to go look at the homework. So in problem number 3, this model is all built around this model that we're studying right now. It's telling you x max is plus and minus 2 volts. And our input is at 0.9 volts. And we have to form the terms, quantization noise power, the signal power, and I'll just throw this up here right now since we're probably going to run out of time. ½ a squared, that's the power of a sinusoid, right? From way back when in circuits. So that's what you use in the modeling that we're going to do here. And we're entering that modeling right now in the notes. So I jumped over to this problem just so you could correlate, pun intended, with the lecture and the homework problems. Good? So I'm going to jump back over to where we are in the notes. So this is our quantization model, and here's a sinusoid model, very much like what's in that homework problem, but there's different parameters in there. So we have a 5 hertz sinusoid, we have a 512 hertz sampling rate, and I compared just a simulation with 3 and 8 bits, so that's 2 to the 3 amplitude levels and 2 to the 8 or 256 amplitude levels. With this simple rounding model. So this is a model in MATLAB. Have no serious worries, but over here in Python, I have a very nice function called simple quant, which goes along with simple spectrum analyzer. So you have this available at your disposal. You get to put in the total number of bits, you get to put in x max, and you get to decide what type of quantizer it's going to be, whether it's saturation, overflow, or none. And overflow is when you have overflow with 2's complement numbers, what happens? The number hits the top, and if it's above a quantization level, it's going to roll around and become a large negative number. So this quantizer produces that nasty stuff if you don't scale it properly. Saturation, though, clips it at the top and the bottom. And none just is like closing your eyes and pretending it doesn't exist. It just lets it keep going up higher and lower. It's like it'll just go right on through. Okay, again, back over to here. The point of this example was to say, okay, there's our sinusoid with 3-bit quantization, and 8-bit quantization is dashed. This is kind of a crude-looking picture. I know I could do much better in Python, but the quantization error, though, is hovering over a range that corresponds to plus and minus delta over 2, just like we've been talking about for the 3-bit. And then for the 8-bit, it hovers over a range plus and minus delta over 2, which is a smaller range because of 256 steps. But the idea here is to see that with only a few bits of quantization, this definitely does not look like a random, uniformly distributed sequence. This looks very deterministic to me, like it's very predictable. When you start getting to more bits of quantization, it starts looking more random-like. So this simple model, although it's pretty crude, it's good for some quick calculations. Are you getting on board with this? This is the error that the quantizer is introducing. And in problem number 3 in the homework, when you get to the very end, you're going to be doing some error calculations. And or problem number 3 in the project, you will see that there is some extra error produced by the finite precision filtering action. So this is kind of trying to justify that we can use this linear quantizer noise model. And if you look at the histogram of the errors, we see that initially with 3 bits, which is pretty worthless, we would quantize to 8 levels a signal. That's like really, really crude sounding. But John has had the opportunity to do that with music or voice or whatever, to actually hear what it sounds like when you quantize to 3 bits. It's understandable, but it's pretty low quality, really low quality. 8 bits is much better. You can see it's much flatter. It's more uniform-like even with 8 bits. So this again kind of justifies that this model is not too bad. It's acceptable. So if we take and use this model, we can come up with this calculation for signal to quantization noise ratio, and this is set number 5, problem 3. It's played right out of this and the previous stuff we've just come through. I would just recommend sticking with this. This is just based on modeling with the uniform distribution and the delta squared over 12. These constants come from the 12 and the delta squared. This has a small advantage, but I think this is just a better way to go. That's the way I work the problems, and that's kind of how I have problem number 3 set up. You calculate those terms that are the power in the signal and the power in the quantization error, and then you get the signal to noise ratio from that. What we see from this is, what you see from this second version, though, is that if B changes by 1, we're either adding or subtracting 6 dB. So that's what bits of precision means in signal to quantization noise ratio. It's going to jump in 6 dB steps as you add or remove bits. One of the things about the quantizer and what I was talking about in the Python model is how do you deal with overflow? Do you have rounding if you have 2's complement? Or do you have saturation, or do you let it overflow and become negative, which is a very gross distorting type error? So you really want to match as best as possible. This was exactly what audiophiles were saying was wrong with the compact disc. They were saying when the compact disc came out with its 16-bit, that quiet passages of a symphony, the gain would be set constant so you could handle loud passages, so the really weak passages would get lots of quantization error on them, and that was going to be noticeable. That there are still people that I think believe that to be true, and it probably is to some extent, but what are you going to do if you start automatically gain leveling everything, then you compress the signal and that distorts it too. So you have to just come up with a happy medium. In the project I worked on, the space radio project, they had a rule of thumb of a 10 dB overhead. So that means you anticipate if the signal maximum level is going to be thus and such, you provide 10 dB more of headroom before you bang against the levels of your quantizer. I have an example in here where what I do is I assume that the signal has got a Gaussian or normal distribution, and I'm going to assume that it rarely exceeds plus and minus x max, because I'm going to use this factor of 3 sigma. So I'm going to say 3 sigma away, and this is a number that I think you see in prop and stats. Only 0.27% of the distribution lies outside of plus and minus 3 sigma. There's some number like that, right, from taking the class? So it's at that level. Plug the numbers into the equation, and we see that with a total number of bits of 16, we get, with this extra overhead, we get 91.3 dB. I think in a compact disc player, when they first came out, they said you'd have 96 dB of dynamic range for music passages. So this is maybe a little bit conservative, but you know, what do you believe? I think some people might say it's higher than 96, but this is just a feel for what sort of things are possible. So, any questions? Because we're fading off into the last homework problem right now with what I'm going to talk about, the D to A to conversion process. Good so far? The equations for that problem 3 are very minimal, very easy stuff, and everybody should be able to get it. The only hard thing is dV, so watch out. You know, if you've got a product of a bunch of numbers, you take the log after you do all that stuff. But if you want to take a product of numbers and take the log of this value and multiply by 10, you can add it to the log, 10 log, the next number. If you're adding and subtracting numbers, though, which you don't have happening here, then you can't do that because logarithms don't allow that. So just watch out for that. Okay, so on the D to A converter side, we have following our signal processing, we have a D to A converter, and we have a low-pass reconstruction filter. So what the book has in it, it says we have a scale when we come out of our digital samples. At the bit level, we're going to scale it by X max to get back to our D to A dynamic range, going to convert to impulses, and then we're going to zero order hold the output. So the zero order holding action is the same idea as the zero order hold on the input side. And I've got a picture of it down here. Well, I guess I don't have a picture of it. Zero order hold just means it's going to hold the output and it's not going to change until the next clock cycle of the D to A. So we have this holding action, which is a constant, which means we get a stair-step approximation, which introduces some distortion. So if you look at it in the frequency domain, we're going to have distortion in our signal, but then we're also going to get quantization noise coming through from other parts of our system interior to it, which we don't have an exact value for, but just we have a fudge number in here. E0 is error and quantization noise from other parts of the system. So we have both of those adding together, and the zero order hold filter is the sinc function. So this is the big bad thing that goes on with a zero order hold in the D to A. You've got this round off in the pass band, and this is why the early compact disc players did the 4x oversampling. We went through that example last week. Remember, we can avoid all that. But in general, what people will do with a D to A is you will buy a D to A, and it might have an inverse sinc function built into it. So it will have something that will shape the output by peaking it up to keep that gain flattening from that roll-off from happening. So that is this guy right here, compensated. It's called an inverse sinc function, and I've seen it in data sheets. So you might see it in a data sheet that says there's an inverse sinc function in the D to A to compensate for that, and this is what it would look like for an inverse sinc function. And then if you could build a really high order analog filter to roll off, you'd be perfect. But of course we can't do that, so then we have to settle for some realizable filter, and that's again, just like on the input side, we were oversampling. We oversample on the output side too, to avoid these issues. So this is just kind of simplistic modeling, and the last problem in the homework is a bonus problem involving a design with a particular anti-aliasing filter, a particular reconstruction filter, and it asks you to come up with what is the design of that filter to compensate for the spectral shape that they give you in the problem. And I'm just going to give you there'll be a comment in the hints page when I push that up, perhaps tonight. Because you've got a roll-off in the spectrum, when you design your filter to roll off and you look at it in dB, it's not going to be a straight line. It's going to have a curvature to it, because a 1 over a slope becomes a parabolic shape. It has a curved shape to it. So just be careful what I did in my solution is I used Python to draw the pictures for me. So, but if you want to hand sketch them, that's fine too. The next topic in here is oversampling A to D and D to A. We're not going to have time to look at that tonight, but this is where I'll get into how a sigma delta or delta sigma converters work. And when that's over with, we have some pretty cool results, and I'm just going to take you for one. And the part that's in the DSP board we're using in the lab right now, and John's not here, but there is an AD in there. It's made by a company called Wolfram, or Wilson, I mean, and Wolfram is part of is a British company, and then it was bought by Cirrus Logic, which is a U.S. company, and that's the device that's on the board. So it's got a 64x oversampling, and so it has digital filters inside of it to do some signal processing. It has the fancy delta sigma that's built into the ADC and to the DAC, and it's got some other digital attenuators or things. So this is pretty much some of the specs on it, though. It just tells you that it can do some audio performance weighting, the mu law nonlinear quantization, but if you want to use it for audio, which is what we do in the lab, it's just running in straight uniform quantization. It can sample up to 96 kilosamples per second. It has different word lengths. We use it in the 16-bit mode, but it has 22, 24, and 32-bit modes. And on the board, this is what the part looks like. If I zoom way in on this, you have a line in, comes in through here. There's some resistors and chip capacitors. It connects to this Wilson chip. And then on the output side, there's a headphone output that can drive speakers and drive earbuds. And then there's also a microphone input, single channel microphone input. So for me and for people that take that class, we look at what does the interface look like. So if you're playing with a board like this, you want to see what goes on at the input. So the line in has got some bypass capacitor and resistor networks. It's got a coupling capacitor. The output side has got a DC blocking capacitor, and then it's got a termination resistor. So if you really wanted to see what's going on circuit-wise, you could model that in LT Spice or something, right? Does that make sense? You'd be able to understand in particular what is this time constant. This is just a coupling capacitor. So in electronics, you learn about how 1 microfarad, if it's a high enough impedance, has a really low frequency roll-off. Because what does a coupling capacitor do? It blocks DC, but it actually rolls off really low frequencies like bass notes or something, right? So you could calculate that time constant, and then this, what this is doing, 220 picofarads and 5.6K. Kind of interesting. I'm not asking you to do that here. I'm just saying that's the type of thing that I look for, and I'm getting a new board here this month now, finally, the GEM, let's see, what's it called, GEM, I forget, GEM something or another. It's a professor in England that designed it for an audio processing course that he teaches to artists and other things, but he's an EE guy, so I'm getting that board from crowdsource. I'm not going to go over anything else, but I will answer any questions. It's 7:17 if you have a project question, or if you just want to ask me on Slack. Homework is probably, now if you were working on the project for a while, you're probably going to have to flip back up to the homework problems. The second homework problem is a random process problem, so it uses that nitty-gritty stuff we were going through, but I'm going to post up a hints page. When you get right down to it, it's not really all that bad. Problem number 2. And problem number 1 is a review from Province Stats. So, and then I ask you to make some histograms and things with that one. Pretty good review, but you get to use Python, so I give you some hints, and tips on using Python for that problem number 1. Are we good?
Yeah.
I'm going to stop.